So hi, in this video we will talk about some rule of thumbs and practical information about the thermal design in power electronics. So let's talk about the relation between size and the thermal performance, and actually it can be quite important for power electronic applications. So my question is, why does the elephant has big ears? For that one, again, maybe the answer from previous years, but it has nothing to do with the hearing ability. It has nothing to do with other purposes. So the main idea of the elephant's big ears is to dissipate heat. So they are basically the heat sink for the elephant. So they have lots of tiny blood vessels in their ears, and actually it helps them to dissipate their heat. So we will today talk about the Squares-Cubes law and its implications in the power electronics. But let's get into the detail. Let's say you have two mice here. Like one of them is a smaller one, and the larger, the other one is, let's say, every dimension is twice of the previous one. And the question is like, who will freeze first? Okay, so I actually advise you to have a look at, go to the original source and read that material. But let's go through that one. Okay, so let's say our mice has just like one unit cube, so it's one dimensions in everywhere. So you can say 1, 1, 1. So in every dimension, so it is one. It has a volume of 1. Okay, so if we can just double every dimension, so again now it was like 1, but this one has a length, that cube has a length of 2. So the problem that we are having here is, yes, you can compare that one. So the volume, okay, so here volume, that is 1, okay, and let's say surface, let's say I don't know, 1, 1, and let's say this is 6, okay, 6 faces. And here you can see the volume now is increased, and volume is increased to 8 because now I have 8 cubes. But surface area is like how much? Like, so you can have like 2 by 2, like 4 areas, and on 6 faces, so it is 24. So basically volume, as you expect, volume increased by cube, okay, and the surface is increased by square. Okay, so one of them is increased 8 times, the other one increased 4 times. So actually this is the squares and cubes law, and it has like many implications in different aspects of engineering. So I mean, one of the reasons why we can't have a space elevator is because actually if you just put a wire up to the space, its weight will be proportional its volume, so it is increasing with the cube, but its strength is proportional with the surface area of that cable. So I mean, even if you can hold the most strong material in the earth, if you can just pull a string of 100 kilometers of that material, it will not be able to carry its own weight. Okay, and again for thermal aspect, the problem is now you have the mass. Okay, so again we have the same problem in the elephant. So now our heat generated in our metabolism, or the heat generated in our power electronic system, is mostly proportional to its volume, okay, the size, and it's the same for elephant. But for elephant, again, the heat dissipation is increasing just by area. So at some point elephant is generating quite a lot of heat, but it doesn't have enough surface area to dissipate that area. So that is why it has those large ears. And actually I again have a look at to those original videos and reading materials, and we have the same relation. We have exactly the same relation for the power electronics. I mean, it can be easy to cool down a circuit at a smaller scale. Let's say if you are designing something for a few kilowatts, it can be easy to dissipate because you have lots of surface area. But if you are designing something in the megawatt scale or 100 kilowatts scale, then the cooling may be a more difficult problem. So that is why you need to be careful about those applications. And in sometimes people designing a small prototype and they can think they can scale everything to a real scale product, but between those scalings of the prototypes, that kind of squares cubes law can have important implications. So again here, you see I think there was an animation in the original presentation, so that is how a elephant looks like without size. Anyway, so for thermal design, in the next week I will supply you some numerical calculations, but the usual roadmap is first you need to choose your components, okay, and then depending on your calculation operating conditions and your components datasheet, so you need to calculate the losses. So if you have a MOSFET, how many watts you are dissipating, and you need to calculate the worst operating conditions. Then you need to find the thermal resistances from datasheet. Again, we will do a practical application, but there are some figures in the datasheet showing like junction to case thermal resistivity, case to ambient thermal resistivity. And again, you can find some suitable heat sinks for that packaging. There are some specifically made heat sinks for similar sized MOSFETs or IGBTs in different packages. And again, you can find the thermal resistances of the heatsink from the datasheet. Okay, then you can decide on the cooling type. Are you going to use a fan, or is going to be a natural cooled? And by having all those numbers, so you can build your thermal network. And usually, again, I will solve a practical exercise, but anyway, let's say this is your MOSFET, okay, and this is your heatsink, and this can be represented as like you have the power losses, okay, not the power output. You need to be careful. Let me write it here. So you can have the power loss of the MOSFET, okay. Then you can have R junction to case, okay. So these will be available in the datasheet, R junction to case. And maybe there can be just one thermal resistance for the heatsink. It can be or R case to ambient for heatsink. Okay, and you can have maybe another one. This will be your ambient temperature, ambient voltage, and this can be like so your heatsink to ambient temperature. Okay, it can be like, let me draw it here. So your first resistance is there. Draw it again. So this can be your R junction to case, and another one will be R case to ambient, and from surface, so it can be high R heatsink to ambient. Okay, so again, by using all those resistances, you can, if you can calculate the power loss, so you can calculate the junction temperature here. This can be your case temperature here, case temperature of the MOSFET, and this can be your T heatsink. Okay, so depending on your power and the distribution of those resistances, you can calculate the operating temperature for all these elements. Okay, so again, here you see a more detailed example. So again, you have a semiconductor here. I mean, this is just the packaging, but actual semiconductor action PN junction is just inside that one. So it is usually shown by the junction temperature, and junction temperature is most of the time the limiting factor. Then you have junction to case, case to heatsink, heatsink to ambient, and the heat is just transferred. Let me use the red. So it's transferred from here to the ambient, and you can estimate how much what is the equivalent thermal resistance and what will be the operating temperature of your power electronic circuits. Okay, again here you see some things, and again be familiar with that kind of definitions. Okay, RJC is junction to case, or I sometimes junction to ambient, or in some cases you have case to ambient, depending on those things, and in data sheets they are usually given with that kind of convention. Okay, so again in the early slides we talk about, up to now we only talk about the thermal resistance, but there is also some heat capacity, and that heat capacity can be small for a junction, but it can be quite large for a heatsink. And again, if you just consider your house, okay, your house, and I just gave that example in the previous video. So you have the walls and you have some heater inside, okay, it just creates some air, and there is some resistance, okay, from let's say wall resistance, okay. And if you model that thing like that, okay, so here's T ambient, let's say this is R wall and this is P heater, okay. Once you turn on the heater, that will be your room temperature, so you expect your room temperature will be 25 degrees immediately. But of course, you know that is not the case. Why? Because you have not only the resistance, but you have the heat capacitance of all the materials. First you need to warm up the air, then you need to warm up the walls and other furnitures, and actually it just behaves like a capacitance, so you cannot increase the voltage of a capacitor immediately, and you cannot change the temperature of a material immediately. There's some lag on that one, so it is like a low pass filter. And for our system, again, there will be some capacitances. If you are just interested in the steady state operation, if this is like some kind of constant DC power loss, of course in the steady state the capacitances will not have any importance. But if you want to have like the transient voltage changes, or how long does it take to reach to the operating temperature, then you need to consider those second order effects. And again, you can find those numbers in some data sheets. Okay, again, it can be neglected for steady state analysis, but for junction, real junction is like really small. If let's say your power loss can be like, I don't know, a square wave form, it can be turning on for 1 minute, turning on, or let's say turning on for 1 second, turning off for 1 second. Again, you can say, in the overall, so instead of calculating all the power through that maximum value, you can say let's calculate from the P average. Okay, that is usually correct, and you can utilize that kind of averaging techniques. But actually for those on periods, due to that kind of small capacitances, the temperature of the junctions or other components can go over the operating temperature. So you need to be careful when doing that kind of calculations. So let's skip that design exercise, and I will post a separate video for that. Okay, so we will calculate those one. So let's talk about the let's go those things, and let's talk about the other tips and other important things to consider when designing our circuits. So first of all, you need to be careful about hotspots and other heat sources. And our lump parameter network is, it is the easiest method, but it just gives you one information about your MOSFET. It can give like this, maybe like 70 Celsius, okay? But if you actually look at the operating temperature, some parts are 60 degrees, some parts are 75 Celsius degrees. So you need to be careful about that kind of hotspots and unequal heat distribution, and if you don't have time or resources for a detailed finite element analysis, maybe you need to put some safety factors to compensate for that kind of non-idealities. And the other one is the layout. So for example, here you see a heat sink and you have other, I don't know, capacitors or inductors, and this is your main heat sink. And if your fan is blowing air in that direction, I mean here it is completely open to airflow, but in the right hand side, I mean what you see is your heat sink is blocked by some components, so it will not get that cool airflow over the heat sink, so you will not get a good performance from that layout. Okay, other thing again, for transients, you need to be careful about low heat components. Actually, I had a graph here, but I think it's not shown here. Anyway, again for airflow, again you need to be careful about connected them like in cascade things mechanically. So here both of the heat sinks getting some fresh air, but here they are put like back to back, so the first one gets the coolest air, but the second one will have slightly warm air. So depending on that warm air, the operating temperature in that second heat sink will be higher. And if you just didn't take into account of that effect, maybe that will go beyond the maximum operating temperature. Okay, and again, if you are just designing for natural air cooling, okay, natural air cooling, I mean it gives like best results to put the fins like that, so the air is get warmed up and it can easily flow in the vertical direction. However, if you can just put the the fins of the heat sink like parallel, then the warm air will be trapped between those fins, and it will not have a nice airflow, and it will have a higher operating temperature even if the power loss is same. The other one is the ambient temperature. Again, for basic calculations, you can get it like as 25 Celsius, but if you are designing something commercial or for military, you need to check the standards, and here are some numbers. I mean, for commercial applications, there are some, again, it doesn't have to be the operating temperature. There are like different sub-standards, but it can go up to 70 Celsius. For industry, it can, the operating temperature can change from -40 to 85, and for military, it can go up to 125 Celsius ambient. So you need to, consider the design criteria. And other things are the non-idealities in the contact surface. Again, you have the heat sink and you have the MOSFET or other transistor. You can put these two metals together, but you have actually not a perfect contact like in the left hand side, but in fact if you can just look at with a microscope, you will have all kind of non-idealities, and because of that thing, the conduction surface area will be limited, so you will have loss of contact here. So that is why we have the thermal interface materials. Okay, so I'm sure you have seen that kind of thermal paste. So it is some kind of silicon material, and the idea is to just fill those gaps. Okay, that is you need to put some, it doesn't have to be like in the liquid form. There's some thermal pads as well which can be squished, or there are some that kind of liquid materials which you can swipe on the surface. Okay, and again there are like adhesive materials, putties. There are some epoxy components, thermal epoxy and potting compounds. I mean, there are lots of different applications, and you can have a look at that one, but you need to be careful about how much paste you put. So here, I mean, again, it is like really insufficient. This is the exaggerated version of the non-idealities in the surface, and the green one doesn't fill those gaps enough. So here you have the ideal thickness, so you don't have to leave any gaps, but you don't have to put like too much thermal paste, because if you have too much thermal pad, yes, you have the, let's say our MOSFET or your switch, and you have the our heatsink, and in between now you put a thermal interface material thing. Okay, so again, if you look at the numbers, that thermal interface is worse than the metal, but the idea is just to fill those things so you will have the maximum contact area for better conduction rate. Okay, so don't just put enough to cover the non-idealities in the circuit. And again, other thing can be like the mechanical strengths, and there's in the data sheets you can find some figures like how to mount those package. Like if you have screws like in this packaging, and if you apply too much pressure, the package will be tilted in that direction. So maybe you are, even if you can apply too much pressure, you can crack the material, you can damage it mechanically. But even if it is not mechanically damaged, you can create some gaps here, and you can reduce the conduction area, and you have bad thermal performance. Okay. And again, you need to be careful about like paralleling devices. Here probably they connected like 4 MOSFETs, or I don't know, other 4 here. Okay, but again, you can say, that one is, doesn't have any neighbor material here, so it can dissipate the heat just from that side. But the ones in the middles, there's some heat coming from that side, and also there's some heat coming from that side. So the operating temperature of the switches at the middle will be higher. So you need to be, careful about those things. And again, if you are connecting many devices into the same heat sinks, you need to be careful about the electrical connections. The anodes or cathodes of those materials can be shorted, and if you are just connecting it to the same heat sink, so you can be connecting them like electrically as well. So you need to be careful about those thermal interface materials. They can isolate electrically while still keeping the thermal performance good. Okay, so again, the most important thing is to read as much as material that you can find, and application notes are really good resources depending on your choice of heatsink and semiconductors. And I just put it here, some links, and you can find those links in the course web page. Okay, so that is all, and you can find the links for those reading materials in the course web page. Okay, thank you.